Hello everyone. In today's lecture, we'll be looking at jump conditions in interface with surface tension. This is a continuation of what we derived in the last lecture. The expression that we derived by taking surface tension into account is given below. It has basically three parts to it. The terms in black represent the hydrodynamic forcing. The terms in green come from the stress tensor. And finally, the terms in the red are the new terms, which are present only when there is surface tension present. In fact, this term actually contains two parts again. The first part that is basically shown as gradient of surface tension. This term is present. Del S of gamma is non-zero only if gamma is varying in space. So for a constant surface tension system, this term does not exist. This term goes to zero. The second term is non-zero only if the interface is curved. Okay. Del S divergence of n, the surface divergence of n, this is the curvature, which is what we have seen already earlier, kappa. We will return to this a little later. So notice that this equation is actually a vector equation. What we want to do in today's lecture is to separate individual components of this equation, a normal component and a tangential component of this equation. Okay. So I want to start by writing down the normal component. So there are a few things to keep in mind. The velocity here u can be thought of as u1, or you can say the normal component un plus two tangential components. We'll call it as um and m plus ut times t, where um and ut are the scalar components of the velocity u in the direction of m and t, whereas un is a scalar component of u in the normal direction. So this has three parts. Okay. So if I want a normal, the normal component of this equation, we'll give this equation a label. We'll call this equation as star. Okay. So if I want the normal component of this entire equation, all I have to do is take the dot product with n and recognize that the dot product of n with m dot is 0. Okay. So in other words, n dot m is 0 because they are orthogonal. And similarly, n dot t is also 0. So only the normal component un of u will survive when I take a dot product of this entire equation star with n. Okay, let's take the dot product with n and see what happens. If I do this, then I straight away get rho. So n dot u minus w can simply be written as un minus wn. And what I have next is un, that is n dot u minus n dot sigma dot n on the plus side. I have the same term on the right hand side, rho un minus wn un. I have the same term on the minus side as well, minus n dot sigma dot n on the minus side. This will be n dot gradient of gamma minus gamma n dot n of del S dot n. Okay. So now let's look at the terms on the right hand side. In particular, let's look at this term here. It's n dot del s dot gamma. Okay. Del s dot gamma is only along the tangent, because gamma is only on the interface and surface gradient of gamma is only along the tangent to the surface, and therefore this term is 0. The reason for that is del s of gamma is only along the tangent, and therefore that term is identically 0. So now what we have is, we have rho un minus wn of un minus n dot sigma dot n on the positive side n dot sigma dot n on the negative side is only equal to minus gamma. N dot n is unity, so I have del s dot n. Okay, let's expand this further, noting that the stress tensor sigma has two parts, a pressure term and a deviatoric stress term. I have minus p times I plus tau. We have n dot sigma dot n will be minus n. I have minus p plus n dot tau dot n. So p is a scalar, so I have n dot n that comes in, and identity n dot identity matrix times n is just 1, and therefore I get this simplification. Now there are two terms here, pressure explicitly and the deviatoric stress term. So if I substitute this, what do I get? I get density times un minus wn of un minus p, but I already have a minus sign, therefore I have a plus p minus n dot tau dot n on the positive side minus rho un minus wn of un plus p minus n dot tau dot n on the negative side. This is equal to minus gamma times del s dot n. Okay, so we'll look at some examples. Okay, for a static case, the velocity u and w and tau, they're identically 0, right? So therefore I get p on the positive side minus p on the negative side. This will be equal to minus gamma times del s dot n. Okay, right? So this is the simplified expression. This is a generalization of the Laplace pressure jump condition, and this can also be written as minus gamma times 1 by r1 plus 1 by r2, where del s dot gamma is del s dot n, the curvature, is 1 by r1 plus 1 by r2. That's the mean curvature, right? So just worth writing this down. This is the mean curvature. This is 1 by r1 plus 1 by r2. Okay. So for students who are not very familiar with the ideas of curvature, I'll give you a very simple way to think about why is del s dot n the curvature. So if you take a curved interface, let's start with a flat interface. In the flat interface, the normal vector is always pointing in the same direction. So when you go along the surface, that is when you go along vary the coordinate s, where s is varied along the surface, then del s dot n in this particular case is 0. This is for a flat interface. Okay. Now when you take the case of a curved interface, del s dot n tells you the variation of n along the surface. now if I take a curved interface, then the normal vector changes orientation along the surface. Okay, and because it changes the orientation, the individual components of the normal vector also change their magnitude. Therefore, del s dot n in this particular case will not be 0 in general. Okay, there are always cases where even for a curved surface, the mean curvature can go to 0. We discussed this in the last class of the example of that pair and a catenoid where the mean curvature is 0 because the curvatures of our opposite sign. Okay, 1 by r1 and 1 by r2 have different signs. Okay, if I think of this again, coming back to this curved surface, the normal vector is changing orientation. Now this is a case where the curvature, you can say, if I were to compare this surface with a surface like this, okay, here the normal vector is changing its orientation much more rapidly. When I say rapidly, meaning for much smaller distances as you go along the surface. Okay, so you can say the first case is a gentle curvature. So gentle curvature, therefore its radius of curvature is very large. In the second case, the radius of curvature is very small. This is high curvature. And you can see that the del s dot n is again clearly non-zero, and more importantly, the normal vector is changing a lot more rapidly as you basically go along the surface. Okay, therefore it manifests itself as a high curvature case. Okay, now we have seen the case of a static case. This is a generalization. P plus minus P minus, we got minus gamma times del s dot n. Let's consider example of a stationary drop. If I think of a stationary drop, assume that this is a circular drop. I have minus here and plus here. The radius of the drop is r. And so what's the result that we got? We got P plus minus P minus is minus gamma times del dot n, which is minus gamma times 1 by r1 plus 1 by r2. Right? And here, for a spherical drop, one by r1 is equal to 1 by r2 is equal to 1 by r, and therefore I get P plus minus P minus is minus gamma times 2 by r, or I get the pressure inside P minus the pressure outside, that is P plus, is 2 gamma by r, which is exactly what we have derived in the last lecture. So this is the Laplace pressure drum across an interface, stationary interface. We'll return to this more with more examples, especially when we discuss capillary statics. Now I want to discuss the tangential stress boundary condition. So let's again recap what we have done here. So we have the equation star here is a vector equation. It has the jump conditions across an interface with surface tension Fx, and we took to get the normal component of jump conditions. We took the dot product of this equation with n. Now we are going to take a dot product of this equation with the tangent vector t to basically get the tangential jump conditions. Let's basically write down the tangential stress conditions. Tangential component, again, there are a few things to keep in mind. Okay, from mass balance, density times un minus wn on both sides plus is equal to un minus wn on the minus side. That's the first thing to remember. Okay. The another thing to also remember is that the tangential velocity is continuous. Therefore, u tangential on the plus side is equal to u tangential on the minus side, right? Similarly, in this particular case, I don't have to worry about um. It will become clear. Um is also continuous, but it will not enter the discussion. Okay. Now, what we will do is we'll take the dot product of equation star with t hat. Okay. If I take the dot product with respect to t hat, what do I have here? I have this entire equation multiplied by t hat. Let's first look at the first term. Okay. That's rho times un minus wn, and then I have u dot t. So let's write that down. I have density times un minus wn times u dot t. So here un minus wn is just the normal component. It is just n dot u minus w. Okay, that's the first term here that I have here. Then I have minus n dot sigma dot t. That's the second term. This is on the positive side. On the negative side, I have rho un minus wn times u dot t minus n dot sigma dot t on the negative side. This quantity here would be t hat dot del s of gamma. The second term here, which is basically gamma n hat, this term is 0 because I have a normal vector. So therefore, this particular component is pointing in the normal direction, and therefore it does not contribute when I take a dot product with respect to t. Okay. So let's now look at this equation that we have. The first thing is, notice that this term and this term, the first two terms are exactly equal. So I can actually, on the positive side and the negative side, they'll perfectly cancel out because it's a product of two things which are equal. Rho un minus wn is the same on both sides because of mass balance. U dot t is also continuous because of tangential continuity of the velocity. Therefore, this entire term I can just cancel them out, and therefore I simply have the result that I have is minus n dot sigma dot t on the positive side minus n dot sigma dot t on the negative side is t hat dot gamma. Now again, if sigma is minus p times I plus tau, then n dot sigma dot t will be minus p times n dot t. That's the first term, plus n dot tau dot t. Again, product of normal with the tangent is 0, and therefore I simply get n dot tau dot t on the positive side minus n dot tau dot t on the negative side. I'll just take the whole minus sign to the other side. I have minus t hat dot del s of gamma. This is basically my tangential stress boundary condition. So I've derived the normal stress boundary condition and the tangential stress boundary condition. Okay. So there are a bunch of consequences of this tangential stress boundary condition. It's a very interesting condition. We'll look at this consequences. Okay. What's the first consequence that we see is there will be a discontinuity of tangential stress across an interface if del s of gamma is not equal to 0. That is, gamma is varying in space on the interface. That's the first observation, that if there is this term del S of gamma, if it is non-zero, then you automatically have a discontinuity in the tangential stress across the interface. Okay. Now, the reverse is also true. If del S of gamma is equal to 0, tangential stress is continuous across the interface. That's the second consequence. There's another important observation. Notice that the right hand side term does not depend on n hat, the normal vector. It depends on t hat. Okay. And this term can be non-zero even for a flat interface. This is not the case for the normal stress boundary condition. The result for a normal stress boundary condition, it's worth putting the result in a big box. Yeah, this is the normal stress boundary condition. Notice that the right hand side has a curvature term. It's a product of surface tension times curvature. So if the curvature term is 0, if curvature is 0, then the right hand side surface tension does not make any difference. Okay. But here you don't need to have curvature. Okay, I'll give you an example. We'll consider the simple 2D flow. 2D, we can call it as a Marangoni flow. Okay, this is an idealized case. So here's the setup that we have here. Okay, so I have an interface here, and on this interface at some point I've arbitrarily called it the origin, and I'm going along x, and the velocity, horizontal velocity is u, the vertical velocity is v along the y direction. Okay, this is a 2D flow. So I can essentially say u of y is not equal to 0. Sorry, it's a simple 1D flow. Meaning there's only one component of velocity and v is identically 0. Okay. Now we'll consider a situation where gamma is actually varying in space. Okay. And how do I achieve that? For example, I could achieve that by actually depositing some soap. If I were to deposit some soap on, let's say, on the right hand side of this interface, meaning, so in other words, when I deposit soap, I actually have surfactant molecules. I'll just show them as surfactant molecules like this. I've basically created surfactant molecules here, but then because of diffusion, the surfactant molecules concentration would vary in space. So there is a certain region where I've actually added soap. In rest of the region, there is no soap, or there's very little soap. So clearly here, because soap molecules or surfactants reduce surface tension. So here, concentration of surfactants is high, and therefore gamma is low. And in the same place, here on the other side, concentration of surfactants is low, and therefore gamma is high. So therefore now I have a situation where I have an interface like this, where I have low gamma, I have a high gamma. And therefore I immediately have del gamma by del x is non-zero, or more importantly, it is less than 0. Okay. Now let's look at the tangential stress boundary condition. This is a 2D flow, simple 2D flow. U is a function of y, right? So I can write down n hat in this case is just nothing but ey, that is the normal vector vertically in the y direction, and t hat is nothing but ex, right? And the stress tensor now has several components here, but only if you were to work out the n dot tau dot T. If you work this out carefully, you'll see that this quantity is exactly equal to del U by del Y. Only one term will survive, where mu is the viscosity. Now here, mu can be either the viscosity of the liquid below or above. Okay, right? So now I have mu times del U by del Y plus minus mu times del U by del Y on the minus side. This is equal to minus del gamma by del X. Okay. Now, for simplicity, it's very clear that if the right hand side is non-zero, then the tangential stress, which is del mu times del U by del Y, is non-zero. Remember, this analysis is only for a special case, flat interface. A flat interface with varying surface tension. Okay, this is not the only way to get variable surface tension. I could actually apply heat on one side and keep the other side either at room temperature or cold. Okay, at higher temperature, surface tension would reduce, and therefore if I want to reduce it, I apply some heat on the right side and less heat on the on the left side, or maybe even keep it at room temperature. Automatically you will actually get a temperature gradient. Okay, and therefore a surface tension gradient. Okay, now for simplicity, if viscosity on the top side is approximately 0, meaning it's negligible compared to the viscosity on the lower side, what I now have is mu times del U by del Y on the lower fluid, okay, is equal to del gamma by del X. And del gamma by del X is negative, right? Del gamma by del X is negative. Now let's basically consider the consequence in terms of a flow. If I basically have a flat interface and I apply some soap here, so this is gamma is actually low here and gamma is high here, then del U by del Y that is produced will be negative, because del gamma by del X is negative for this case. And immediately I will have, the moment I apply soap, the fluid basically will be driven in the opposite direction. Meaning fluid regions of higher surface tension is creating a stress along the surface. It's creating a stress along the surface, and this stress is basically pulling the fluid from regions of lower surface tension to regions of higher surface tension. Okay. There are many other interesting phenomena associated with these Marangoni effects. So, such as tears of wine. Hopefully we will be seeing a video of this phenomena and an explanation that goes along with it sometime later in the course. This term here explicitly, this term, you can also call it the Marangoni stress. It's commonly referred to as the Marangoni stress. This is because of gradients in surface tension. Note that gradients in surface tension can either come from temperature gradients, it can come from surfactant gradients. You can also have Marangoni effects when you actually have a mixture of two fluids with different surface tension. For example, if I have a mixture of alcohol and water, we know that alcohol is more volatile than water, and therefore and at the same time the surface tension of water is more than alcohol. So in regions where, let's say, alcohol evaporates, there locally the concentration of surface tension becomes more, and there you can actually create a variable differential surface tension, and such mixtures of two fluids can also lead to Marangoni stresses. Okay, all you need is a gradient of surface tension. Okay, so just to quickly summarize what we saw in today's lecture, we saw that starting with the general jump conditions at an interface with surface tension, we derived the normal component of it, which is basically which has pressure, and it has on the right hand side it has the curvature term. And for the case where a static interface is reduced to what we'd seen earlier for the Laplace pressure jump, that the difference in the pressure will be surface tension times curvature, but now the curvature is del S dot N. In a later lecture, we will see how curvature itself is calculated for an interface. Then we looked at the tangential stress condition. In the tangential component, we saw that the difference in the tangential stress is equal to what is called as the Marangoni stress. Okay. So this Marangoni stress leads to, if there is a gradient in surface tension, it leads to a flow. Okay. Now this is the third consequence that I want to highlight and end the lecture today. If del S of gamma is not equal to 0, okay, a stationary fluid is not possible since there will be a non-zero tangential stress on the interface. We know that fluids will flow when you subject them to a tangential, when you apply a tangential stress. At the interface, if there is a tangential stress, the fluid will immediately respond. The fluids on both sides actually will immediately respond by flowing. So the moment you create a Marangoni stress, you cannot actually have a static fluid. Okay, a stationary fluid or a static fluid is incompatible with a Marangoni stress. Okay, that's a very, very important third consequence. Okay. So we will end this lecture. So now what we have done in the last few lectures is we have derived the jump conditions at an interface, both with surface tension, without surface tension. The equations in the bulk are the mass and momentum balance, that is the Navier-Stokes equations for incompressible Newtonian fluids. Okay. So now we have the equations in the bulk. We have the boundary conditions or jump conditions on interface. Now we have all the necessary machinery to actually address some interesting problems in interfacial fluid mechanics. Thank you.